Alrighty. So it looks like some folks are trickling into our session here. With that, I think we'll get started. Welcome to our conversation on transportation safety and roadway design. Let me know if you have trouble hearing me. I cannot tell if I'm connected to my headphones or not, but I think I'm in good shape. Awesome. So, with that, we have six presentations today with six different speakers. With that, we're going to try and do our best to keep to time. We're going to be going in these presentations sequentially as shown on the order of your screen here. And then we'll have time for questions right after each presentation for a few minutes. But I would also encourage everyone to put their questions in the chat. It can be during the presentation as well as following that, so we can have questions lined up for our speakers right when we get to that point. I'm Melissa Ryan. I'll be moderating this session today, and I'm an assistant professor at Michigan State University, and I study transportation safety. With that, I'm excited to dive right in and welcome Sam, who will be presenting testing models of traffic safety culture in Lethbridge, Alberta, using contemporary factor analysis and structural equation modeling. With that, Sam, I'll pass it off to you.
All right, right on, Alyssa. Thank you. Can everyone hear me okay?
Yes, we can.
Brilliant. And can everybody see my screen?
Not
Can
yet.
anybody? Okay. Yeah, that's because I'm not sharing. All right, folks, how about now?
Looking good.
Excellent. Okay, yeah, so as Alyssa mentioned, my name is Sam Pollock. I'm presenting today on behalf of a big group of people from Martinson Golly, which is a small consulting company in Western Canada, and the Schulich School of Engineering, the University of Calgary, also in Canada. So I'm going to be talking a little bit about today on different models of traffic safety culture in a mid-sized Canadian city. So I'm not going to belabor the importance of traffic safety here. We're all in a academic presentation or session on road safety, but needless to say, there were 1,900 traffic deaths in Canada in 2023, and those numbers are not going down. It's higher numbers of deaths and serious injuries since pre-COVID. And different levels of government, federal, provincial, municipal in Canada have all been trying to tackle this issue. Um, and what we see is traffic safety culture is an area with increased interest for its potential for improving road safety outcomes. And one definition for traffic safety culture is given by the National Cooperative Highway Research Program. It defines traffic safety culture as the values and beliefs shared among a group of road users and stakeholders that influence the decisions to behave or act in ways that affect traffic safety. So we're really looking at that interplay between someone's belief system and their attitudes and how that affects how they behave on the road. And you can see it's kind of growing in importance and interest. One way to look at that is the number of different Canadian municipalities that have adopted traffic safety culture as part of their Vision Zero or safety plans. So I'm going to talk about two different models that model traffic culture safety, traffic safety culture rather. And there's been a number of different ways this has been done, but one of the leading models is this integrated model by the NCHRP presented in 2018. And as you can see, it's fairly sophisticated. There's a lot going on. It's based on previously established and validated behavioral models. And at the basic level, the model states that willingness and intention contribute to behavior. It's the belief system and the values that feed into this. And then your values and belief systems are formed by your social environment, which exists at multiple scales, everything from you as an individual to maybe your friend group, your immediate family, all the way to the municipality and the country you live in. So you can see there's a lot of different things going on here. It's a theoretical model, but it's one of the kind of the leading ways we understand traffic safety culture. Now looking at a slightly different model here, this is an empirical model developed using survey data from a Canadian city called Edmonton. In this model, we've got four different latent constructs, so threat to personal safety, self-reported behavior, support for enforcement, support for law and policy. And importantly, this model can be seen as supporting part of that big model on the previous slide. So, we can see that the concept of threat to personal safety is an attitude, and it really feeds into behavior. So similar to what we see in the NCHRP model. However, there's a key difference in that there's more interplay between the belief system here. So in the NCHRP model, we see that all the beliefs are feeding in directly through behavior, or at least through willingness and intention. Whereas in this empirical model by Islam et al., it there's more interplay in the belief system. And the size and complexity of the NCHRP model makes it unlikely that one study is going to validate it. More likely, you're going to see studies like this one that are either validating or supporting a part of the NCHRP model. Okay, so that's a little bit about what some other folks have done, but what about what have we done? So this study was conducted in Lethbridge, Alberta. Alberta is a province in Western Canada. Lethbridge is a city of about 115,000 in the south part of that province. It's a regional hub for agriculture and food processing. If there are any of my American friends in the audience, Fargo, North Dakota is kind of a good comparison city if you're trying to think what is this Lethbridge. So worth noting that the previous study done by Islam et al. Presented on the previous slide was done in the provincial capital of Edmonton, so about 500 kilometers up the road from Lethbridge. And then this study was part of a broader project related to traffic safety culture. It was funded through a Transport Canada grant and led by Martins and Golly. Okay, so the specific objectives for this research project were as follows. We were trying to measure traffic safety culture in Lethbridge. We're trying to investigate support for two traffic safety culture models. So that's the big integrated NCHRP model, as well as that empirical model by Islam et al. And then we're trying to identify some methodological improvements for future researchers and practitioners. So this research is fairly exploratory, fairly early stage, and we're trying to see what we can do to think about this and do things better in the future, both academically and practically. Okay, so how did we do it? We used a polling firm to conduct a telephone survey of 400 Lethbridge residents. The survey had questions about four types of driving behaviors. So there was aggressive driving, speeding, distracted driving, and impaired driving. And so each of these types of behaviors had different behaviors attached to it. So for example, for distracted driving, we had using a handheld device and talking on the phone while driving. Those were the two specific behaviors that fell into the distracted driving type. So we're looking at four types of behaviors, and as well, we're looking at five latent constructs. And so these five latent constructs are self-reported frequency of behavior. So how often are people saying that they're doing or engaging in the behavior? Perceived danger of the behavior, perceived norms of the behavior. So that's if people perceive these behaviors as accepted in the community. Perceived likelihood of enforcement. So that's if people thought that it was likely that these behaviors would be subject to enforcement action. And then control beliefs. And control beliefs are essentially beliefs that people have related to their ability to control a behavior or not. Measuring control beliefs turned out to be a little bit of a mess. So they were excluded from most of the analysis. If people are curious about control beliefs, happy to talk about them during the Q&A. But the big idea here is that we tried to measure these. It didn't work very well, and so they were excluded from the analysis. And then in terms of how are we analyzing these five latent constructs, it's through confirmatory factor analysis and structural equation modeling. Here's an example of some of the data. This is just to help people wrap their head around what we were working with here. You can see this is for the specific behavior of speeding on residential roads. So the behavior is speeding on residential roads. The behavior type is speeding. You can see, so we've got our four latent constructs here. So self-reported frequency, we can see that most respondents were either never or rarely engaging in this behavior, and then some were sometimes, often, and always engaging in the behavior. And you can see here that this is a Likert category that was collapsed. So for any Likert categories where we had fewer than 15 respondents, or responses, I should say, we would collapse it until we had enough. And this was just to ensure stability while estimating the models. And in some ways, this is a good thing, right? If to have fewer respondents engaging in these behaviors is a good thing. Perceived danger, so follows kind of the opposite trend of what we'd see for self-reported frequency. So there's some respondents that view Speeding on residential roads is not at all or slightly dangerous, where others view it as extremely dangerous. Perceived norms. So, most respondents think that others in the community would strongly disapprove of the behavior, while some think that there are people in the community that people in the community generally strongly approve of speeding. You see a little more even distribution on perceived enforcement likelihood, so people are divided on if enforcement action is likely to be taken against someone speeding on a residential road. So this is what the data looks like for this one behavior. And again, we've got 10 of these associated with the different behavioral categories. Okay, so using these results, or using the data, I should say, we estimated a measurement model. So we did some confirmatory factor analysis. For those unfamiliar with factor analysis, the basic idea is that we're trying to see if these different indicators, so for example, questions about speeding, running red lights, using a handheld device, etc., reflect the latent constructs that we're interested in. And in this case, we're really testing if we can measure a general concept of perceived danger related to traffic safety or perceived norms related to traffic safety. And this is worth testing because it's not immediately obvious that these things will all, these indicators will all load on to the same construct here, right? Like arterial speeding is actually could be a very different behavior than driving after using cannabis, for example. However, after looking at the results of the factor analysis, things are pretty solid. These 10 behaviors do load onto these four latent constructs pretty well. All the loadings were statistically significant. Almost all of the loadings, so I should say all but three, were greater than 0.5. Got solid fit indices. One thing to note, though, is due to the estimator used and some missing data, our sample size here is actually 276 instead of the 400 people polled, and we can talk a little bit about why that is in the Q&A if people are curious. Okay, so it's good. That's great. We've got a measurement model. Our latent constructs are are valid or supported by the data at least. But the really interesting thing here is how are these constructs related, and do the relationships align with those found in existing models? And so this is where the structural equation modeling comes in. And as a reminder, we're trying to see if the Lethbridge data mesh with the integrated model, the complicated thing that I showed earlier, and then the empirical model from Edmonton. And so let's start with the complicated NCHRP model. It posits that attitudes through willingness and behavior, which isn't or willingness and intention, which aren't shown here, drive behavior. So this is a very simplified part of the NCHRP model that we're trying to validate or support. And then this is what we ended up with after using our correlations from the factor analysis and then testing different model specifications. So you can see there are some things that agree with the NCHRP model. For example, perceived danger is associated with self-reported behavior, but there's more relationships going on in the backgrounds. These perceived norms and perceived enforcement likelihood. There's relationships within the factors, but not directly on self-reported behavior. So again, we're seeing more interplay within the belief system than we saw or than you'd see in the NCHRP model. Now comparing our data to see if it fits well with the empirical model. So a reminder, this is what that looked like. These things can be considered within the belief system, and then we've got the self-reported behavior here. And you can see that our data really supports this model pretty strongly. Especially, we've got that link between perceived danger and self-reported behavior that was found in the previous study. So broad support for the modeling work done by Islam et al. In Edmonton. Couple discussion points. So based on these models, okay, what can we take out of this? So there's varying rates of self-reported behavior. So some things like speeding, more people reported engaging in, whereas some things like, for example, driving under the influence of cannabis, very few respondents reported engaging in that behavior. Perceived danger was consistently associated with a decreased rate of self-reported unsafe driving behaviors in both models. And then there's weaker relationships between the other latent constructs and the directions, and the causality for sure in those relationships is a lot less clear. So we've got some support for the NCHRP model, or at least that influence of danger on, which is an attitude on behavior, and then broad support for Islam et al.'s model. All right, so what does this all mean? Some practical implications and some future research calls here. So one is that perceived danger and self-reported behavior are related. This kept coming up in the results. But one thing to caution against is this doesn't mean that fear-based messaging is the answer. So before practitioners go all in on fear-based messaging, it's important to remember that there's a body of literature out there that indicates that messaging with fear doesn't work consistently, doesn't work in the long term for reshaping behavior related to unsafe driving. We need more work related to measuring control beliefs. We followed the procedure outlined in the NCHRP report, and it didn't work for a number of reasons. Happy to kind of discuss that, but there needs to be more work in figuring out how to measure these and how to understand them. And then finally, traffic safety culture work would benefit from more studies and especially larger sample sizes. One thing that is posited by the research here and there, but not kind of broadly understood is heterogeneity in traffic safety culture. And that's both in terms of scale, so how this changes from, say, a group of friends to a city to a country, as well as geography. So, this shows that there are similarities between Lethbridge, Alberta, and Edmonton, Alberta. But what about other Canadian provinces? What about cities elsewhere in the world? How does that change? So, a lot of unanswered questions there related to bigger sample sizes and more studies. So just like to thank everyone involved in the study, my co-authors from Martins and Golly and the University of Calgary, as well as staff at the City of Lethbridge and the team at Y Station Communications that helped with this. I'm happy to take any questions, and of course, if you're interested or have any questions, you can reach out to me academically or at my consulting email address. I'm happy to get in touch either way. Thank you.
Brilliant. Thank you so much, Sam. With that, if you want to raise your hand and verbally ask a question, that would be great. You could also place your question in the chat. Give folks a minute to do that. And maybe I'll kick us off. Sam, could you talk a little bit more about what you envision for your next steps for this project will be? Like, what are you going to do immediately next steps for that?
Yeah, I mean, so for Lethbridge, what ended up happening was, some of these results informed a traffic safety transformation plan for the city. So the city's using some of these findings to kind of help shape traffic safety culture going forward there. And then I think the hope for us is that we get to run similar studies and larger studies and better studies in different cities to better understand how traffic culture, traffic safety culture, is different in different places, and then how it can be transformed and shaped to ultimately improve road safety outcomes.
I love that. I feel like your presentation is the perfect one to kick off this conversation because it gets back to that central theme of like convincing, I guess, the larger world how important this is and how it's everyone's responsibility. It's not just the data we're showing, right? It's everything. It's changing the way we think. And so, yeah, I really appreciate that. I don't see any questions coming in. So, Sam, would you be willing to put your email in the chat? And so, if folks want to circle back with you, they are able to. Oh, Paul has a question. Paul, please unmute and go for it. Paul, we still can't hear you. Do you want to unmute? Thank you.
Okay, all right. Okay, thank you so much. Thank you, Sam. Thank you for the great presentation. Ryan, thank you for the opportunity to say two things about his presentation. It was quite enlightening, quite interesting. I was involved in a similar research of recent, but I used machine learning algorithms to do some classification. And the research work encountered a lot of challenges in terms of sample size. Looking at the population of this location, and then the sample size, I think it's about 200 and something or about 120 something. I can't recollect exactly. But then I want to find out how were you able to navigate through this sampling to be able to add value to this research? Because most reviewers out there who question the population, were you able to, how did you arrive at this sample size? That's my question.
Yeah, I mean, so in that way, well, actually, I'll start by addressing something else you mentioned there, Paul, before answering your question. We also took a machine learning approach to this early on. We tried to do some clustering analysis of the data, and we did not have very good success with that. We couldn't find very good, kind of clear subcultures or traffic safety subcultures. So if someone's able to do that well, I'd be very interested in seeing it or seeing a data set that worked. In terms of sample size, it was somewhat freeing because it was based on what the city could afford. So the city said we have budget for 400 responses, and we said, okay, that's what we're going to get. So we didn't have kind of the liberty of figuring out what our sample size should be. We were just given what it was going to be and then worked with it from there.
You were constrained by the budget. That is what it means.
Yes, exactly.
All right. Okay. It's fine. Thank you. Thank you.
No,
Awesome.
thanks for your
Thanks.
question.
As we all are always constrained by our budgets, are we not? I would have 1 million people in my study if I could have the money for it. Brilliant. Well, thank you so much, Sam. Really appreciate your presentation. Thank you for putting your email in the chat as well. We'll move into our next presentation, which is a grid-based approach to counting vulnerable road users from video data, presented by Mubarak Thanni, which at this time, I believe if you want to share your screen, we can move into our next presentation.
Are you able to see my screen?
Yes, but it is not in presentation mode on our end. We're seeing the last slide and it's in kind of the PowerPoint. There we go. Now it's in presentation mode, but we're still on your last slide.
Sorry.
All good.
Yeah.
Perfect. Ready to go. Take it away.
Yeah. Hi, everyone. My name is Mubarak Thanni, and this work is with my advisor, Dr. Suman Mitra at the University of Arkansas. So I'll be presenting a grid-based approach to counting vulnerable road users from video data. So this is my presentation outline, going from the problem and what data we use, the results, the findings, and conclusion on our findings. So the problem is about collecting data of pedestrians and bicycles, counting them. So we see the trend of, even with the advent of computer vision, researchers are still using pneumatic tools and inductive loop to count pedestrians and bicycles, even with the cameras that we have, enough cameras that we have. So the problem is actually coming from the fact that object detectors that are currently out there, maybe YOLO and other detectors, they don't have like 100% accuracy. So without this 100% accuracy, if you use a detector to count, it propagates that errors into, even before getting to the counting stage, it propagates this error into the tracking. Then from the tracking, you get errors in your counting, large errors. So this is like showing what I mean. This is from a study that used intrusion line. So intrusion line is when you try to detect the intersection between the centroid of the object that you're counting, that you want to count, say person 13 in this image now. The centroid of this person, when it crosses the intrusion line, that green line is an imaginary line. So that means it counts that line. But at that particular time, it is possible that the detector fails. And when the detector fails, the tracker will fail, then the person will not be counted. So we are trying to provide a solution to this, that, okay, with the current accuracy level that we have for machine learning, for computer vision algorithms, can we improve counting accuracy? So that is what this work is all about. So we are proposing a grid-based counting approach. So if you see in this on this slide, for human observer from point A to point G, a person will be able to detect those red lines. They are just assuming that they are like pedestrians or bicycles or something or riders. So the person will be able to count 6 people at point A, and for human observer, the person will be able to count up to point G that, okay, this is like 6 people, which will be correct. But for computers, if you allow the intrusion line to count, the place you are drawing that imaginary intrusion line, at that point, if something happens, then even though 6 people are crossing on that line, to be like 4 people are crossing. So that is so we are now proposing an approach to maximize what the computer is saying. What this even though we have failures at different points on the grid, can we be able to trace them back? So the aim is to demonstrate the use of grid-based counting to counting vulnerable road users, which are very difficult to count compared to like cars and vehicles generally. So the objectives is to perform detection, object detection, to perform tracking, to apply the grid-based counting, which will be like our contribution here. Then the last part is to compare the current line-based counting to the grid-based counting. So to start, we looked for the biggest data we can find because we're not interested in counting only pedestrians. We want to count all vulnerable road users. So most detectors are primarily designed for pedestrians or bicycles alone. So we wanted to count like all vulnerable. So we found this data from Europe. It's the largest data we were able to find, about 47,000 images. It contains data for all riders, whether they are riding buggies, bicycles, different kind of things, and pedestrians. So then we combine that with, that is our image data for object detection. Then to track, we need to test our tracking. So we combine 3 video data sets we were able to find. The first one is a very popular data, the K1 data. So it's a data from, if you are familiar with multiple object tracking challenge website. So we took a video data from there. Then we took 2 video data from Bexar's website. So those are our test data sets. This is the method we applied. So because it was not just pedestrians, we are applying 2 object detectors and 2 object trackers to be able to single out our own grid line contribution, like grid line count contribution. So for YOLO 11X and YOLO 26X, these are like the largest version of these YOLO models, but they were pre-trained for pedestrians only, mostly for pedestrians and bicycles. We were interested in doing more, so we had to transfer that learning based on our data. So we took the already trained YOLO 11X and already trained YOLO 26X and performed transfer learning with our data to train the data again. Then we used popular byte track and bot sorts. There are some of these are like one of the two popular object trackers out there that are like performing well. Then we compare the errors from the intrusion line and then the grid-based counting. So for the intrusion line, we have the algorithm. I'm not presenting the algorithm here is a long algorithm, but we have definitions of how tracks will be retraced, like different tracks that are lost will be getting back. So we have different rules with which this is like a set of rules. So some of the important ones that I will mention is this longest common subsequence. It looks for the track that is very related to what has been lost, then it marks that tracks. So we have different thresholds for all these variables. The dwell time, if somebody comes into our detection window, how long can that person stay there before we are going to assume that, okay, maybe this person is just waiting, or the detector will not even count that person at all. So to put into like for you to understand properly, so we have all these parameters, and these are like a parameters search based on the video images that we have. So we developed this parameter search. So we did calibration on each video set, each video test data that we have, and everything you are seeing here is based on optimization from minimizing the error between the human observer and the actual human observer and what the grid is saying. So I'm going to get there in a couple of minutes. So whatever this calibration gives us, whatever the result gives us, we use that in subsequent parts of the video to confirm whether the result is valid or not. So this is like the version for calibration. So this is the setup, like this is for video K1. So we defined this area of interest, then the red line is the intrusion line. So this area of interest is that part that we are bringing the grid. So it's divided into different grids, different set of grids. I show that here, like 10 by 10, 5 by 10, 2 by 10, different sets of grids. So it is the optimization that will select. For this particular K1, 10 by 10 was selected for both sorts, and 10 by 2 was selected for by track. That one is just based on what works well for each detector and tracker combination. So this is the setup for the tracking and counting, and this is set up for tracking and counting. So we did that. Then for our results, so that is like the method. For the results, for object detection, we have like I said, we use YOLO 11 and YOLO 26X, and it is expected. We're not expecting 100% accuracy. So we perform this training to a stable training to make sure that the learning, the precision, and the recall is stable. And we have these F1 scores. From here, we can see that F1 scores for pedestrians is more than the rider. This is like largely based on how the dataset is structured, because the dataset has about like 80% pedestrians and 20% riders, even though after we oversampled for riders. So this is like some of the detections on the validation set, validation data, daytime, nighttime. We have different kinds of scenarios in this data. So we just evaluated how our model is performing on different cases, whether it is performing well on maybe snow time or rainy weather or something. So we have this, and we achieve like a uniform performance across like all cases. So this is like the most interesting part of our study, showing the results from the grid-based and the intrusion line. So what I have in bold here, K11, K12, then K21 and K31, they are the parts of each video that we use for calibration. So for example, this the red line, this red part, this red bars and other parts of the bold videos set of the video KT is used for calibrating that video K1. So whatever the calibration result gives us to minimize the error between what human observer is counting for each video segment, we use that calibration result to estimate what it will count for the remaining part of the video. So to put it better, from 0 seconds to 80 seconds, this is based on the calibration results. Like we have performed calibration there. Then from 80 to 160, we use the calibration result to see whether it will continue to perform well for video K1 data. Then for video K2, we did similar thing. That one, we just divided that into two, 0 to 31 seconds to perform calibration, then 31 to 54 seconds to evaluate what the calibration has gotten. So this is for YOLO 11 results, what we obtained from YOLO 11. So what we have here, E1, E2. E1 is the error between what human observer, average of what human observers are seeing, and what the intrusion line is seeing. Intrusion line. So E2 is what the error between what human observer is seeing and what the grid is seeing. So if you look at what E1 is saying, you see in most cases, the errors are larger than what the E2 is showing, meaning that there are like missed detections on the intrusion line method. So for YOLO 26, so the result is very similar to what we have in YOLO 11. So it's almost like very, very similar because YOLO 26 is just like a modified version of YOLO 11. So we summarize this result based on root mean square error, and we have that if you look at what we have here, the intrusion line for both sorts for YOLO 11 is 9.05, but when it comes to grid-based, it reduced to 2.73. And likewise for YOLO 26 from 7.64 to 3.27. So this happened too for the bi-track tracker. So we also did the MAE, and we have similar results too. You can see the grid-based result is showing a better performance compared to the intrusion line counting. And also the MAPE, the same thing. We have better result for the MAPE too. So to summarize and to conclude on this study, we did this grid-based counting approach, and we found that it consistently reduced counting errors compared to the intrusion line counting algorithm. So the reduction is consistent, irrespective of the detectors, whether it is the YOLO 26 or YOLO 11, and it's also consistent irrespective of the tracker, whether it is both sort or by track. So this study has applications to transportation agency in the sense that most agencies, most DOTs in the US that I know are still using pneumatic tools and inductive loop. They are not trying to make use of the cameras available to try to count pedestrians or count bicycles. And that is because of the errors that is coming from using those cameras to count. So for limitations, we manually defined this region of interest, and for scalability, it will be better if this is like automated to define the region of interest for like every intersection, because it will be difficult to define for many intersections the way we did. So performance on the highly congested movements, like we didn't estimate, we didn't evaluate what if we have like congested pedestrians or vulnerable road user movements, or if the camera is moving, because that is very, very important. If camera is shaking, the recording camera is shaking, then our region of interest, our grid-based area too will shake, and that will create some problems in how we design that region of interest and how we design the grids too. So also, we did not evaluate the difference between the domain from the image data, because the image data that we used to perform the object detection was obtained from the UK, whereas the test video was gotten from the US. So we did not evaluate the domain differences, maybe in the background, UK background, or this thing. We are just evaluating that, okay, pedestrian in the UK will also be equal to a pedestrian in the US. I think that will be all. Thank you. If you have any questions, I will have them now.
Thank you so much for your brilliant presentation. Again, folks can raise their hand if they have any questions, and you can then unmute. You could also place your question directly in the chat. With that, I'll pause and wait for any questions to come through. Maybe I'll start us off just kind of thinking about spreading the word on this conversation. Like, I feel like this isn't something we talk about a lot compared to other conversations. How are you kind of documenting this and moving it forward to make sure it's brought to more audiences?
Sorry, I would just say that to simplify this thing is just all about reducing counting errors and comparing what the current method is doing, the intrusion line current method, that okay, is missing detections. If you just use a line, the detector may not see that line, may not work while that object is crossing on that line. So, but if you use an area, you will see it. So the way we our approach to this is let the detector see many times, let it detect many times, so that when it sees this object many times, then it will be able to track and arrange that, okay, this is one person and I'll just count this one person. Instead of just saying, okay, detect this pedestrians or this vulnerable user at just one point, in which case it can fail at that one point.
Thank you so much. And we do have a question from Paul. Paul, do you want to unmute and ask your question?
Mubarak.
Yeah.
It's another interesting one. It got me thinking when you presented the techniques. I could see that extensive presentation on this topic. Yet, I'm curious to find out, what do you think YOLO better machine learning approaches, like the convolutional neural network? And is it long? There are a few that are used for image analysis for the trimming process. So I just wanted to know why the YOLO. I know YOLO is very popular, but in your context, was there any comparison? What actually informed your choice of
Okay. Yeah, so object
YOLO?
detectors are generally classified into whether they are going to be, okay, sorry, are you done with the question?
Yeah, I'm done.
Oh,
I'm done.
oh,
Yeah.
okay.
What actually informed your choice of using YOLO? The question is, what informed your choice of using YOLO?
Yeah. So object detectors are like in two categories, like maybe three categories, I would say. Single detector, single stage detectors, two stages, and the transformers. So for YOLO, which means you only look once, so it is applicable if you want to go real time. And you mentioned CNN. Most of them, most of these object detectors their backend is based on CNN to convolutional neural network. It's based on CNN. So what informed using YOLO? Number one, is faster. Like it's faster than using two-stage detectors because it detects these objects and classify it just at the point of seeing this object. So it's fast in detecting. So if you use other two-stage detectors, you may be working with heavy detectors that will not perform in real time. Though this object has not been done into real time, but it is possible because we use YOLO, it is possible to move it close to real-time applications.
Okay, thank you.
Yeah.
Thank you.
Awesome. Well, thank you so much, Paul, for your question and Mubarak for your presentation. With that, I'd ask you, if you don't mind, to put your email in the chat should any other questions arise from folks. They'd be
Sure.
able to get a hold of you. That would be
Sure.
great. Fantastic. And we'll transition now into our next presentation, which is Patterns and Predictors of Total and Fatal Injury Crashes in Bexar County, Texas, a decade-long spatial temporal study by Mahbuba Ahsan. If you want to start sharing your screen.
Yes. Can you see it?
Yes, it isn't yet in presentation mode, but I can see your screen. Brilliant.
Thank you very much.
Take it away.
Good morning, everyone. I want to thank BTR for giving me the opportunity to talk about our decade-long spatiotemporal study on total and fatal crashes in Bexar County, Texas. And I'm Mahbuba Ahsan. I'm a doctoral candidate in the Department of Civil and Environmental Engineering at University of Texas at San Antonio. And this work was co-authored by my advisor, Dr. Hatim Sharif. And I'm gonna start my presentation. So I'm gonna walk through this in 7 sections. So first I'll start with the motivation and research gap. I'm gonna talk about study area and data. Talk about the three methods that we have used, spatial, temporal, and severity modeling, and discuss those results with you. And finally end with the conclusions and practical applications. So let's start with the motivation on why we chose to study the Bear County crashes. As we all know, traffic crashes are a leading cause of preventable injury and death in all parts of the world, but especially it's very concerning in Texas metropolitan counties, and Bear County is the fourth most populous county in Texas with more than 2 million population, and we have fewer studies that combine a full decade of crash data and also look into the spatial, temporal, and other factors that may affect these crashes, and to systematically intervene to avoid these preventable injury and death. So that's why we have designed our study to fulfill three objectives. First, to identify the hotspots, meaning we wanted to locate the high risk locations and statistically significant crash clusters. We have used kernel density estimation and local indicators of spatial association, or LISA, to identify the hotspots. Then we wanted to examine the temporal trends, and we have done that by descriptive distribution of the crash frequency and severity by hour, day, month, year, and other specific factors such as the roadway factors, weather, lighting, and behavioral factors. And finally, we wanted to model the crash severity to develop a statistical model to identify the environmental, vehicle related, and demographic predictors of crash severity. So this is the study area. This is Bear County, Texas. This is located in South Central Texas, and it has a heterogeneous landscape uh, with an urban core, suburban ring, and rural periphery. And it has a dense network of interstates, arterial corridors, and local roads. And as Bear County has a diverse regional economy, it produces varied tra- travel behavior and mobility patterns. And that's the reason that we have many crashes in this area. And so the data that we used for this study was obtained from Texas Department of Transportation Crash Records Information Systems, otherwise known as CRIS. So that has different tables for the data, crash, and the persons involved in the crash, and the vehicular unit, and other environmental informations recorded and reported by the on-duty police officer. And we have also used the rainfall data, the NCEP stage 4 multi-sensor precipitation with about 4 kilometer resolution matched to each crash's location and time. And we have done this study for 2013 to 2023. That's 11 years. And so we have done this for the whole Bear County crash population. So methodologically, we used three complementary approaches: the spatial analysis, temporal trend analysis, and severity regression modeling. So I have talked about this in the objectives. So these are the methods that we used to find out where the crashes are occurring, when and under what conditions they are occurring, and what predicts a fatal outcome. So let's talk about the spatial methods and the results that we got. So first, we have done the kernel density estimation. So to find out or estimate the density of crashes, we have used the bandwidth of 1000 meter. So this bandwidth was chosen as the balance between spatial detail and surface smoothness. And we have tested sensitivity for this bandwidth, and we have checked like with 500 meter, 1000 meter, 2000 and 3000 meter to see whether the hotspot shift or not. And we have seen that the hotspot persists in the locations that we found. So the sensitivity was tested, and we have found some like medium and high concentration tires. After that, we have done another analysis because the densities uh, don't tell you about the statistical significance. They just tell you like where the clusters are, but whether those clusters are significant or not. To test that, we have first done the global Moran's I as a precondition for local indicators of spatial association, and the results from the global Moran's I, we found that the clusters were not random and they were statistically significant. So as our next step, uh, we went ahead and did the Lisa clustering, and we found the hotspot. Now let's look at the results of the hotspots. So we have seen from the kernel density estimation and also the local indicators of spatial association clusters that uh, persistent concentration in the downtown San Antonio area, um, and also along with the loop 1604, loop 410, and also I-10 corridors, they have the persistent concentration of hotspots or like crash hotspots. And when we looked into, this is for the total crashes, and when we looked into specifically for the fatal crashes, we have seen the picture is a bit different and more concerning, because you can see all the hotspot that we had here, they are present here, but we have seen that the petrocrush cluster are growing or strengthening in some regions. For example, in the southern and the southeastern tracts, they have been strengthening over time. So for 2013 to 2016, those were diffuse, those are not very significant. But in the later years, from 2017 to 2023, they got much more strengthened. So that means our uh, focus for the fatal crash hotspot have been, the range had been increased. Now let's look into the temporal results. So for Bear County, we on an average for this decade-long period, we on an average day we have 157 crashes with the standard deviation of 34 and the range from 43 to 374. And for the fatal crashes, it's 1.3 crashes per day. And the number that is going to give everyone a pause is that we have 0 days with zero fatalities across this entire decade. So you can imagine how bad the situation is. Even though the population is high, the city is growing, we have to think about this number, which is very concerning, and we have to take targeted actions to address this. We also looked into the yearly and monthly patterns of the crashes, and we have seen the persistent upward trend in local total crashes, and we have seen a visible dip in 2020 because of the COVID situation. But the fatalities peaked at peaked in 2022. And for the months, we have seen that August is the lowest crash month and October is the highest for both total and fatal crashes, likely because of the holiday season and also having the schools and all offices open at that time. Um, so that's the yearly and monthly patterns. We have also looked into the weekly and hourly patterns where the difference between total and fatal crashes emerge. So for total crashes, we have seen that they steadily increase Monday through Friday, and they peak during afternoon commute hours. But for the fatal crashes, they are proportionately higher on weekends, and they peak overnight, especially between 2 a.m. to 3 a.m., which tells us that when exposure is low at that late hour, it doesn't mean the severity would be low. We have seen here the severity is high that time. So that's an interesting finding from here. And we have also looked into weather, lighting conditions, collision types. I'm not going to read through all these categories, but basically what we found, it tells us about the same story that uh, the uh, the conditions that increase the exposure don't necessarily map onto the conditions that increase severity. So that brings us to the severity model itself. So we have done an ordered logit or proportional odds regression. Because crash severity is an ordered outcome, we have from no injury to fatal injury crashes. So we have done the ordered logit regression, and we have included roadway and environmental factors, person-related and vehicle-augmented factors. For example, the vehicle age of the driver, different fatigue factors, drug, alcohol, speeding, distraction, use of restraint. So we have used those on the whole population of the study, and we have also done checked the stability. So what does the crash severity model tell us about the predictors? So we have seen that you can see these predictors, uh, like dominant predictors in serials. So we have involvement of the pedestrians, involvement of pedal cyclists, involvement of motorcycles. That means the vulnerable road users, unrestrained occupants, drug, fatigue, speeding, and alcohol factors. And these are all significant at the level of p-value less than 0.001. So that's what tells us about the dominant factors of the crash severity. But that but let me translate these coefficients into something more intuitive, which is the predicted probability shifts, because only the significance value or the coefficient values do not represent how how dominant they are statistically. So to see that, I have this chart over here for the percentage point shifts, and so the average shift in our predicted fatal crash probability, when we selected the baseline at 0.4%, we have seen when we have the pedestrian involvement, it raises the fatal probability 20 times over the baseline. When we add the motorcycle, it becomes 11 times. When we add the unrestrained occupant, it becomes 7 times the baseline. So that basically told us that the person or the vehicle factors dominate crash severity by an order of magnitude over every roadway or environmental factor tested. So the factors that we have previously thought, like the weather or the roadway infrastructures, those are more significantly affecting the frequency and severity of crashes. We are seeing a slightly different story here. We are seeing that the involvement of vulnerable road users is very, very serious here, which is understandable because as I live in Bear County, I myself have firsthand experience that there are not sufficient pedestrian or vulnerable road user friendly infrastructures here, which we definitely need after these findings. So the key findings suggest that we have the stable and persistent crash concentrations in the downtown San Antonio along the major loops and the highways of our county. And we have also found out when these crashes occur. And also we have seen like which factors are more dominant, which factors we need to take care of to avoid the fatal crashes. So let's talk about the practical applications. The findings from this study tells us that we need to have geographically targeted enforcement and investment. We have to prioritize the hotspot regions. And since we also have identified the times when the crashes are getting at their peak, uh, it becomes easier for the law enforcement and the city planning department to take care of those extra number of crashes and fatalities to avoid that. And we need to ensure the vulnerable road user protection. As I already have told you, we need more crossings, protected lanes, lightings, where the vulnerable road user involvement drives the largest fatal risk increase in the model. We also have to promote the seatbelt or restraint compliance campaigns uh, to avoid those fatal outcomes, and work on the impairment and fatigue countermeasures, since those are the reasons uh, most likely that is causing the nighttime fatal crash peak that we found. So we have some limitations, and I want to be upfront about that. So the severity information that we got is officer assessed at the scene. It's not medically confirmed, so it may call for potential misclassification. Then we have used the census tracts for the special analysis, which is subject to the modifiable aerial unit problem, and we haven't used any traffic exposure data in the study because the available volume data is annual and county-wide. So that is too coarse for these studies, daily, hourly, temporal, and also spatial scale. So in our future work, we intend to integrate higher resolution exposure data as it becomes available. And thank you. I'm open for questions and discussions now. My email address is noted here. If you want to discuss or have any questions later on, you can send me an email. And that's all, gonna be all from me today.
Thank you so much. Again, just a reminder for folks, if you want to put your questions in the chat, but you can also raise your hand and unmute to ask any questions. I want to start off. This is really important conversation. So we know that data, the way data is reported in safety can sometimes be not full, right? Which you've talked about. What are some ways in which we can start to uncover how many crashes may be drug involved or how many crashes may be distracted related? Like, are there other techniques that we're seeing that we may want to start to consider rather than only police reports? Because right now we're probably not capturing them all.
Yes, definitely. Yeah. So we can also engage the medical facilities when the crash is fatal. We have that. So that linkage we haven't covered in this study yet. But yeah, definitely that's a future plan, and we intend to do that. But yeah, the medical facilities and to be honest, over the recent years, this the quality of this data has been like very much improved. Uh, uh, because of the involvement of TechStart, it is getting more and more intensive, and we are like more and more trusting on this. But definitely, the medical, that's what I told. Like we haven't checked with the medically confirmed data, but that's another way to incorporate.
That's great. I agree. It'd be interesting to someday look at kind of the trends on, because we often look at the trends right from year to year, but often we're also just uncovering more data now than we were before. So it's not necessarily that we're seeing an increase in some things, it's just that we're like better at collecting it. That caveat's so challenging though to talk about, because we really don't know. But no, that's great. I'm glad to hear the data is getting better. At least for some states, that is very solid. Again, if any folks have any questions, you can also put it in the chat. Do you mind putting your email in the chat as well? That way folks can reach out to you and they have that information. Awesome. All right. With that, we'll move into our next presentation. Thank you so much again. Awesome. Fantastic. So our next presentation is exploring the impact of roadway lighting on driver behavior and road safety. And we have Kyla Lee here to present. With that, I'll pass it off to her and she can take it away when she's shared her screen.
Can I see my screen?
It looks like it's starting to share, but it hasn't quite popped up for me yet.
Okay, I will just double check it a little bit. Just stop sharing
Yeah,
share again.
sounds good.
Mm, Still cannot see the screen?
Not yet. It does say you started to share your screen, but it's stuck on that page.
That's kind of weird. Mm, I will try another way here.
Sounds good. And just so folks know, we do not have our oh, it looks like it's working now. We do not have our last presenter here of today, so we're in less of a rush now. Unfortunately, that person could not make it. So for our last two presentations, we have more time for discussion now. With that, kind of looks like your presentation is showing well. If you want to take it away.
Yeah, thank you, Dr. Rain. So hi, everyone. You can see my screen, right?
It looks like it's just trees now, but we were just seeing your presentation before.
Okay, it's just like I'll show it again. Don't only still not. I'm sorry for that.
Oh, you're fine. Technical difficulties never seem to go away. I run into them every day, so
That's true. Okay.
awesome. That's looking good. You want to give it a
Yeah,
test?
yeah, I will just like move to next slide to see whether it's working. Okay, sounds good.
Perfect.
Yep. Hi everyone, sorry for the delay. So my name is Kelly and I'm a PhD student from UT Austin. So today I will be talking about exploring the impact of roadway lighting on driver behavior and road safety. So this work is done by me and also my supervisor, Dr. Kockelman. So as a background, uh, mm, although nighttime travel is only 25% of vehicle miles traveled, but the fatality rate is almost 3 times higher than daytime. And in terms of pedestrians, they do have a higher risk at night. Almost 75% of US pedestrian deaths occur between 6 p.m. and 6 a.m. So roadway lighting has been developing as a potential countermeasure which can improve the visibility, help drivers detect surroundings, and also protect vulnerable road users, which include pedestrians and cyclists. So I will talk a little bit about existing research here. So although the research report mixed effects on average speeds for roadway lighting, but they do have helpful benefits for the crash reduction. So it shows the roadway lighting can lower crash frequency and also severity, especially for vulnerable road user related crashes. So one research pointed out that the benefit cost ratio is about 2.6 to 5.6 at unsignalized intersections, and the value becomes 2.8 to 7.9 at signalized intersections. So for now, we brought up three research questions here. The first one is how does lighting affect large-scale speed distribution and speeding patterns? And the second one is what are its impacts on intersection versus mid-block crashes? And the last one is how effective is lighting as a real-world safety countermeasures? So I will be introducing several data sets we use in our research. And the first data set we use is the street lights data for city of Austin in Texas. And here is a map showing the spatial distribution of the roadway lighting in this city. And in total, there are about 65,000 light poles, and also most of them concentrated in urban and downtown areas. So to assign these ports to corresponding road segments, we used a 30 feet buffer here. And to represent the lighting for each roadway segment, we use the lighting density, which is the number of ports per mile, to include as a model attribute. And another data we have been relying on is Texas speed data. So for here, it is an INRIX data, which includes 2 million to 4 million vehicle trajectory data in Texas, which catch about 4% of total vehicle miles traveled. And in this study, we use 1 month sample here, which is November 2024. So the table shows what the data looks like, and we will mainly use the speed data under the trajectory field. Oh, and this figure shows the number of vehicles on Austin roads by hour of day in the whole month. And in total, we have about 15,000 INRIX segments, and we included about 2 million segment level hourly speeds in our final model. And I have to mention here is that the INRIX data do have the data bias. For example, the light duty and also the heavy duty vehicles may be underrepresented in the database, while medium duty vehicles may be overrepresented in our database. But for now, we are not addressing this issue in this research. And another crash data we use is from text.cris data, and we covered about 138,000 crashes over the past recent 10 years. And we found that the share of vulnerable road user related crashes is highest from 6 p.m. to 9 p.m., reaching up to 6% of total crashes. And here is a figure showing Austin's total and also vulnerable road user related crash counts by hour of day. And since our model includes intersection crashes and also mid-block crashes separately, so we define our intersections as nodes with more than equal to or more than 3 connected INRIX segments. And we use the intersection flag to classify the intersection crashes versus mid-block crashes. And the intersection flag is already indicated in the CRIS database. To answer the last question about the effectiveness of roadway lighting in real world application. So for here, we also develop try to find the study sites in Texas. So we finally got 43 treated versus 57 control corridors in Texas. And when we try to figure out the control sites, we use the following criteria. The first one is it needs to have the same number of lanes and also speed limit as the treated sites we have found. And the second one is they need to have a similar AATD within a 20% threshold. And all of the sites needs to be more than a quarter miles long. And all the treated sites, they already installed the roadway lighting. So we define our before period as the January 1st, 2018 to the lighting installation date. And the after period will be the start date through the last day of 2025. And since roadway lighting is only operating during the nighttime, so we also define the active time as the sunset to the sunrise time based on each site's location. And so we are using that based on the latitude and longitude of each corridor. So finally, we are using 30.8 million hourly segment level average speeds from Retix data and also 27,000 crashes from CRIS data based on almost about 100 corridors here. And for other data sets we used to build our model, we got our roadway design data from textile roadway inventory dataset. And we also include information about the school zone and also block group land use data and also weather data. So for the weather data, we got it from the US Geologic Survey to get the detailed wind speed and also the temperature for each location. And now I will move to the final results. The first result will be the average, the speeds. And we use a weighted least square model for different kinds of roadway type. So for here, the table shows the model estimates for local roads. To account for the spatial autocorrelation, we constructed a spatial weight metric using 1 divided by the distance between segment centroid within 1 mile. And we can see from the table that the average speeds and also the average speeds are higher during the nighttime, especially on arterials. So on arterials, the nighttime we have about 5 mile per hour higher speeds. And to get the how the lighting will change the speeds, we use attribute as an intersection between nighttime and also lighting. And we do see that for each additional pole per mile, the average speeds decrease about 0.04 mile per hour on collectors and the local roads. But for arterials, the reduction is not that significant. Among all other attributes, we found that speed limits is the most significant attribute affecting the average speeds and also 85 percentile speed and 95 percentile speeds. So we found that with 1 standard deviation speed limit increase, the average speeds increase about 21% to 35% across all roadway classes. So for here, we conclude that more lighting can have a lower nighttime speeds, especially for the lower class roadways. And now we move to the speeding share. So we use 3 thresholds here to represent the speeding vehicles. We try to catch the share of vehicles speeding over the speed limits and also those exceeding speed limits by 50% and also 30%. So we use a binomial logistic model to estimate that, also based on different type of roadways. And for here, we found that during the nighttime arterials, the speeding share about 50% higher. And for the interaction between the nighttime and lighting, we also found that for each additional pole per mile, on local roads, the speeding share decreased about 1.6%. And for arterials and also collectors, they do have a very slight decrease. And among all other attributes, we found that the two-way configuration and also urban setting are the 2 most significant attributes affecting vehicle speeds, affecting the speeding share. And in terms of the temporal attributes, we found that on Sunday the speeding vehicles share rise about 32%, with keeping everything else constant. So for this part of our model, we conclude that although the more lighting can lower the speeding share, but they do have like a not that significant impact compared to the speeds. But the reduction in speeding share are very obvious for the arterials. And in terms of the to answer the second question, we create a crash count prediction model. And for here, we try to separate our daytime and also nighttime crashes based on the latitude, longitude, and the specific date. And for here, we use negative binomial model separately for intersection crash counts and also the mid-block crash counts. And I need to say here is that a little bit different from mid-block crash counts. For intersection crash counts, we include attributes both for the major and also the minor approach. And the identification of major and minor approach depends on the AADT value, speed limits, and also the number of lanes. And for here, it shows the crash outcomes for the model. And here we found that the nighttime do have a 30% fewer intersection crashes, but for the mid-block crashes, it has a slightly reduction on that. And for the lighting density, we found that one standard deviation increase in the lighting density corresponds to about 16% more crashes and 10% more crashes at intersections. So it means that that high-risk intersections actually receive more lighting. And when we see the coefficient for the interaction attributes, we found that the intersection has 13% fewer crashes, both for the total crashes and also the vulnerable road user-related crashes. But for the mid-block, we saw a slight increase. So why the mid-block has higher crashes is because like we put the product of AADT and the roadway length as a variable as well. So the increase may reflect reduced turning movements and also the fewer intersection conflicts after dark. And for other attributes, we found that the most significant variables affecting the number of intersection crashes is the number of approaches approaching the intersection and also the urban setting. While for the mid-block crash counts, the product of AADT and roadway segment length and also urban setting are the most significant ones. Regarding the land use variables, we found that more population and also job density corresponds to more crashes both at intersections and also mid-block. So for this part, we conclude that lighting is most helpful in reducing crashes at the intersections, especially for vulnerable road user-related crashes. And now we move to the last model results. Is for the case study. So for here, the plot shows the average speed change in treated sites versus control sites. And we do see that there is a smaller increase in the treated group during the after period. And to create the model for that, we also generated the hourly flow based on our 1 month INRIX probe data, and also use that to scale to match the AADT values. And also like to specify the lighting treatment, we split them to 3 periods. From sunset to 11 p.m., 11 p.m. to 2 a.m., which is the bar closing time, and also the 2 a.m. to sunrise. So for here is the final model of our speed equations. And we do include site level random effects here. And here is the speed outcomes of the case study. And we found that the lighting treatment is statistically insignificant increase in speeds. And the speed limit is actually the strongest predictor, corresponds to about 10% increase in speeds with 1 standard deviation increase here. And also the presence of curve and higher network density and higher traffic flow also associated with lower speeds. And for the year variable, we do find that the speeds increased during the COVID year and also after that. And here is the plot for the total nighttime crash rates in treated sites versus control sites. And we do see a smaller increase as well in treated group during the after period. And for here in the model equation, we introduce exposure attribute, which represents the vehicle miles traveled multiplied by the number of days. And for the model results, we also found that the 19 is statistically insignificant for the total and also the total vulnerable road user-related crashes. But we found that the 19 can have a notable decrease in intersection crashes here. And lastly, I will do a brief conclusion of our work. So we found that the roadway lighting can help slower the nighttime speeds, especially extreme speeds and also on local roads. But the share of vehicles speeding didn't change that much. And in terms of the safety outcomes, we found that the roadway lighting can lower the crash rates at intersections, especially crashes involving vulnerable road users. And comparing to the case study, we found that the crash savings and also speed reductions are actually bigger in our cross-section regression analysis than the before and after analysis based on 100 corridors in Texas. And for here, I would say like our future work would be try to estimate the real lighting based on the pavement and also nearby, and we can add more days of the year to get our speed and speeding equations more accurate, and also obtain more treatment sites with the lighting added in recent years. And I think that will be it. Thank you for listening to my presentation, and I'm open to any questions here.
Brilliant. Thank you so much for your great presentation. Really interesting findings as well in terms of like those specific changes. I wouldn't expect kind of the overall speeding to change, but then the number of vehicles kind of being the same. That was pretty interesting. Looks like we have a question from Michael. Would you like to unmute and share your question?
Sure, yeah. Thanks. Great presentation. I'm wondering, second to last conclusion was that in the cross-sectional analysis, it does seem that lighting is an effective tool, whereas the before-after analysis, the more, I think, stronger causal analysis technique suggests that there is really no impact at all and potentially an increase in crashes and severity with lighting. So what do you make of this? What do you think explains the discrepancy there? What's the next steps to try to do more analysis here?
Yeah, thank you for the question. I mean, like the statistically insignificant results also like surprise us at first, but I think the main reason is like we only include 100 like treated and also the untreated sites in our case study. So I would expect we need to definitely obtain more treatment sites to get more reliable results here. And also, I would say another thing here is that since our speed and also the crash analysis are only based on these 100 corridors, so since we include many attributes in our model as well, so I would say like we definitely need more data based on that to get a more expected results, I would say.
Thank you so much. We have another question from Mubarak, if you want to unmute.
Yeah. Hi, thank you for this great presentation. I was wondering, I saw in your model that's when you were using days as variables, you use Monday as like the base variable. I was wondering why you did that instead of just doing weekdays and weekend. Then my second question is, you mentioned that you obtained weather data for each locations. So because these locations are very close to each other, like maybe a few miles. So how did you get whether like what unit of location did you use for this weather to allocate it to each location in your analysis?
Okay.
Thank you.
Yeah. I mean, like I can just like answer the second question at first. So, are you referring to the study locations in our case study? So, like I would say like the corridors we picked in our study sites are very like far from each other. So I don't think that they are very close to each other. And I
Okay.
hope that solves your question. And by the way, what's like the first question again?
You use Monday as a base variable in your model, like as one of the variables, but Monday was the base variable. I was wondering why you didn't do why Monday as the base compared to others instead of just weekdays and weekend.
Oh, okay. I mean, like for the I think for the data we saw, like they do have like, oh, I will just go here. Okay, this one is just for show like the hour of day. But in our database, we do saw like there are more traffic on Monday because I feel like people need to commute, and we do saw like the speeding share, actually they do have like a higher speeding share on weekends. I think that because like people will go out for fun.
Okay.
Yeah, thank you for the questions.
Yeah.
Brilliant. Well, thank you so much for your presentation. I think that's a really interesting kind of like human factors question as well, getting at Michael's question of like why is this happening? Kind of unclear to me too. I think that'd be pretty interesting to look into some more behavioral perspectives on that, so maybe some surveys in the future. Well, thank you so much for your presentation, and we'll move on to our last presentation of this session. Do, 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 do. And that would be analyzing school zone speeding using vehicle telematics data, a case study in Charlottesville and Albemarle County, Virginia. And we have David Feng here ready to present that. With that, I'll have you share your screen and we'll make sure we get through those technical parts before.
Sure, yeah. So let me just hit the presentation button, and can you guys see my presentation?
Yes, you're good to
Okay.
go.
Perfect. So, hello everyone, this is David Feng, and I'm gonna present my presentation, the analyzing school zone speeding using vehicle telematics data, and a case study in the Charlottesville and Albemarle County area in Virginia. So a quick introduction on the author. So this is me, David Feng, and my advisor, Professor Brian Pott, and also another author who is also like a co-author, another professor in our university, Professor Andrew Moonshine. I don't know if they are here, but they are nice guys. And okay, so let me start. So why the speeding is very important and why does the school zone speeding matter? So speeding is a persistent roadway safety problem, but it's especially concerning in the school environments because students and other vulnerable users are concentrated in a relatively short period of time. And also high school zones also have a particularly complex traffic mix. In addition to buses and parents drop-off traffic, they also include like student drivers who may be less experienced, as well as like commuters who are simply traveling through the corridor. Also, many high schools are located next to arterial roadways with relatively high normal operating speeds. Drivers may therefore need to make a substantial speed reduction when the school zone limit become active. And the problem is visible locally. So in 2025, so this line is from a local news report. So automated cameras outside two Albemarle County high schools issued nearly 11,000 fines. And these two schools are in our case studies. And this suggests that the school zone speeding in Albemarle County and Charlottesville City remains a significant issue, even when there's like a enforcement already present. So some research gap and objectives. The existing school zone studies have provided valuable evidence on speed compliance, enforcement, and safety outcome. However, many of these studies rely on roadside observations, camera reports, or aggregated speed statistics. So these results for sure can tell us how many violations occurred, but they often provide less information about the behavior of individual vehicles across time and space. So the good news is that our study addresses this gap by using high frequency vehicle trajectory data. And this allows us to examine the vehicle level speeding during the flashing periods and differences across campuses and time periods, as well as school access versus passing by traffic, and whether there's like repeating speeding drivers. So in other words, the main contribution is not simply identifying that speeding occurs, but also identifying where, and where it occurs and which type of trip contributes to it. So before going to the methodologies, so let me just make some definitions so that people can understand my presentation. So we examined like 4 public high schools in Charlottesville City and Albemarle County. And so the first definition is we call the school zone road segments or school zone roadway segments. So it is defined as the roadway segment beginning at the flashing school zone speed limit sign and ending with the corresponding the end school zone sign. So these 2 photos, can you see my, oh, you can see my mouse. So these 2 are the photos I took from Albemarle High School. So this is like the flashing school zone start sign, and you can see here, this is the end school zone sign. So the segments in between these 2 signs are defined as the school zone roadway segment. And we use the latitude and longitude coordinates of these signs to identify the geographic boundaries of each school zone. And these locations were then matched to the corresponding OpenStreetMap way IDs so that the relevant roadway segments could be extracted from the trajectory data. And therefore, when I refer to school zone speeding, I'm referring to the like the speeding vehicle behavior within this boundary, rather than like all the roads located near the public schools. Also, another definition is called flashing period. So it refers to the scheduled time when the flashing beacons, these 2 yellow lights. These 2 lights are active, and during this period, the applicable posted post speed limit is reduced to 25 miles per hour in Albemarle County and Charlottesville City. And a non-flashing period refers to the time when the beacons are not active, for sure. So I will be talk about the details of when they flash in the next slide. So these are the sites that we study in our research. So we have at the Albemarle, we have 4 public high schools: the Albemarle High School, Western Albemarle High School, Monticello High School, and Charlottesville High School. So at the Albemarle High School, the regular speed limit is 35 miles per hour on a road called Hydraulic Road, and the other one is 30 miles per hour on Lamps Road. So this school has 2 school zone roadway segments. And then both of them for sure reduced to 25 miles per hour during the flashing period. And you can see at the Western Albemarle High School, the non-flashing school zone, the non-flashing PSL is 45, and then reduced to 25. At Monticello is 35 to 25. For the Charlottesville High School, it is pretty different because it does not have a flashing school zone sign. So instead, the surrounding roadways are permanently posted at 25 miles per hour. So in our research, we treat this school as a 24/7 flashing period. And you can see also for these 4 schools, the flashing schedules are different. So now I'm gonna introduce the data we use. So the analysis used a high frequency connected vehicle trajectory data collected over a 14-day period in April 2022. And the sample included 10 weekdays and 4 weekend days. And the weekdays corresponded to normal school sessions, which means there's like no spring break or no Easter break. So each vehicle generated a trajectory observations approximately every 3 seconds, and the available variables in the dataset include a timestamp in year, month, day, hour, minute, second, very accurate. And latitude, longitude, instantaneous speed every 3 seconds, and also an OpenStreetMap roadway segment identifier called the WayID, also an anonymized vehicle ID. So we first identify the target points located on the school zone roadway segments and within the geographic boundaries of each school zone. Now I'm gonna introduce 2 definitions of speeding. So the primary classifications was conducted at the vehicle level, and the vehicle was classified as aggressive or reckless speeding if it has at least 1 trajectory observation exceeding the relevant speed threshold. within the school zone roadway segments. So for aggressive speeding, we define that as means traveling at least 10 but less than 20 miles per hour above the PSL. For the reckless speeding, it means that traveling at least 20 miles per hour above the limit. This is consistent with the law of Virginia, their definition of reckless speeding. So this slide summarizes the analytical workflow. So first, we filter the trajectory data using the OpenStreetMap VIDs within the school zone roadways segments. And then we just restricted the points to the geographic boundaries defined by the school zone signs. Second, the observations were classified by operating conditions, including flashing and non-flashing periods, and by morning flashing period and afternoon flashing period. So there are two flashing periods. One is for a student going to school. The other one is for the school dismissal flashing period. So the third one is each vehicle was assigned as an aggressive or reckless speeding if they speeded. And finally, we used under geofence to distinguish vehicles that enter the campus access roadways from vehicles that only travel along the adjacent roadways. So this allows us to separate the school access vehicles from the vehicles just passing by the roadways next to the school. And so from this slide, I'm gonna present some results we found from our data. So this is our first major result, which is the non-flashing versus flashing period. So the aggressive speeding was substantially more prevalent during the flashing period at all three schools, where a non-flashing comparison was available. So at the Albemarle High School, the percentage increased from 31% to 71% during the flashing period. And as the Western Albemarle High School, it increased from only 5.1% to 78%. That's a huge increase. And at the Monticello High School, it increased from 1.9% to 42.8%. So for the Charlottesville High School, it remains because it has a 24/7 flashing period, there's still aggressive speeding for 25.4%. And for the reckless speeding, it was concentrated at Albemarle and Western Albemarle High School. And the highest value was observed at the Western Albemarle High School. There's like a 15.3% of reckless speeding vehicles. So these results suggest that many drivers did not reduce their speed sufficiently to comply with the lower school zone speed limit. So therefore, the flashing controls did not necessarily ensure the speed compliance. So, because many vehicles appeared during both the flashing and non-flashing period, and the observations are therefore paired. So we use a Mars test to compare the paired vehicle level speeding classification during the two periods. So just a quick introduction on how the Mars tests were using in our research. So here the value B represents the vehicles classified as speeding only during the non-flashing period, and C represents the vehicles classified as speeding only during the flashing period. So the null hypothesis is that the two counts are equal, and a significant result indicates that the vehicle level speeding classification differs between the two operating conditions. And the pair results were very clear. So at the Albemarle High School, there's like 146 vehicles were aggressive compared with during the flashing period, compared with 25, and similar results in the Western Albemarle High School and the Monticello High School. So, and also the p-value shows up below 0.001, which we think that's statistically significant. And the reckless speeding result also shows a similar pattern at the Albemarle and Western Albemarle High School. Therefore, we can conclude that the higher flashing period speeding prevalence was not simply suddenly caused by observing a different mix of vehicles. So among the same vehicles, the classification as speeding was significantly more common when the lower school zone speed limit was active. So this is how we interpret the differences across the schools. So the magnitude of speeding problem differed considerably across the four campuses. So for Western Albemarle and Albemarle High School, they showed highest aggressive and reckless speeding prevalence. And one plausible explanation is that the surrounding roadway context, because I just posted the screenshot from the Google map of the two schools. So this is the Albemarle High School, and this is the Western Albemarle High School. So at the Western Albemarle High School, the school zone segment is like in this yellow roadway. So the regular speed limit is 45 miles per hour, but it suddenly drops to 25 during the flashing period. So this 20 miles per hour transition requires a substantial and timely reduction in speed. So some drivers may recognize the active school zone too late, or they may not decelerate sufficiently before entering it. Also, for the Albemarle High School, the roadway segments are here and here. So it is also located in a higher volume material environment. So this can be the similar interpretation. However, for Monticello High School, it's located on narrower and more curved roadways, so which may naturally moderate speeds. And for the Charlottesville High School, it locates in a residential area, so the operating speed may already be lower. So these interpretations suggest that the school zone treatment should be site-specific rather than identical across all the campuses. And another result is that we compare the morning and the afternoon flashing period. So the first table compares all the vehicles entering the school zones during the morning and afternoon flashing period. And the second table here compares only the school access vehicles during the two periods. So at Albemarle High School, the aggressive speeding increased from 58% to 69%. And at Western Albemarle High School, both values were pretty high in both periods at approximately 75% in the morning and 74% in the afternoon. So this indicates that the speeding problem at Western Albemarle High School is not only limited to one school zone window. So the Monticello High School has a different pattern. So the aggressive speeding decreased from 45.5 to 29.5%. And Charlottesville High School for sure remains lower overall. And overall, the temporal pattern depends on the campus. So this suggests that the intervention focus only on either the morning or the afternoon may be insufficient. So we have next results. So we then focus on the morning period only for the school access vehicles versus the passing by vehicles, because the morning period coincides with the school drop-offs and the broader AM commuter peak, because the students may be worried about being late for their first bell, and also parents dropping off the children, they might be late for their school, which may generate some trip chaining. So across 4 schools, 582 vehicles were observed during the morning school zone period, and about 19% entered the school access geofences. So the remaining 469 vehicles were classified as passing by traffic. And because the passing by traffic was much more numerous, so they represent a larger absolute component of the observed morning speed. And the aggressive speeding was identified among 59.5% of the passing by vehicles compared with 53.1% school access vehicles. However, the percentage by school tells a more nuanced story, which is the table here. So more than 50% of school access vehicles were classified as aggressive speeders overall. And at Albemarle, Monticello, and Charlottesville High School, the aggressive speeding percentage among the school access vehicles was actually higher among passing by vehicles. This means that those who drop off and park at the school also have aggressive and reckless speeding. And they know the school flashing period policy, but they were still speeding. So this indicates that speeding was not caused by only unrelated corridor passing by traffic. So some school affiliated people's trips also contributed meaningfully to this speeding problem in Charlottesville City and Albemarle County. So we also analyzed the timing of morning school access speeding. So this figure aggregates the school access speeding trips across weekdays in 5 minutes intervals. So we can see at Albemarle High School and Western Albemarle High School, so which is this and the blue one and the orange one. So the speeding trips were clearly concentrated around 8:30 a.m. in the morning, and Albemarle High School and Monticello High School showed another noticeable increase between approximately 8:45 and 9 a.m. So this temporal cluster suggests that the school access speeding may intensify during the later portion of the arrival window when parents or student drivers may be concerned about arriving before the start of the school. So also we analyzed the repeated speeders. So vehicles were classified as repeated speeder if they recorded more than 2 aggressive speeding during the morning study period. And you can see there are like a great number of people who are repeated speeders. So therefore, the repeated aggressive speeder was not widespread among all regular school access users. Instead, it was concentrated within a relatively small subset, particularly at the Albemarle and Western Albemarle High School. So some implications that what we can do for this. So engineering treatment should reflect roadway context. So at locations with large speeding transitions, like Western Albemarle High School, driver may need clear advance warning. And also some enforcement should be targeted rather than uniform, which means they should be different for each campus. Also, some engineering and enforcement alone may not fully address school athlete speeding because there is some like repeated speeders. So we need some school-based education or direct outreach to the parents. Also, we can manage the arrival time for say students arrive later so that to release some morning commuter pressures. So to give you guys a quick conclusion, so this study uses high-frequency vehicle telematics data to examine school zone speeding around 4 high schools. So there are some limitations in our research that the study covered only 14 days and 4 schools. The telematics sample represents only observed connected vehicles and it not randomly sampled for all traffic. Also, we have some factors that weathers are not available. So for future research, we can use a larger data set or we can get the weather data to be considered as a factor of speeding. So however, overall, this study demonstrates how vehicle trajectory data can provide a more detailed understanding of when, where, and why people speeded across the school zones in the Albemarle County and Charlottesville City. And that's it. So thank you guys, and I will welcome any questions from you guys.
Brilliant. Thank you so much, David. Really appreciate that presentation. Again, if you would like to unmute and ask any questions, just raise your hand. You can also put questions in the chat. We still have 5 whole minutes to move forward with questions. And Brian, I see you put your camera on. I know you were the advisor on this project, which is great. Did you want to just share any other thoughts on this project or kind of your vision for next steps?
Thank you. Thank you for asking that question. David might have a better answers than mine, but use of telematics data is emerging, obviously, and we can actually have a lot more detailed informations. And I'm hoping that people willing to opt in share their personal data. Hopefully, parents wanting to have a high school kids driving and then monitoring their data and find way to improve safety. And there's many different opportunities to use this kind of data. And probably the key is removing the concern on Big Brother privacy issues. And we have to let them know how exactly we are using that data. And then they need to be comfortable to opt in.
Yeah, that human problem is massive, right? Building those partnerships. Gosh, I
Yeah,
don't even know how to go
exactly.
about that. David, do you have any other comments on that?
Yeah, so for the data we are using, all the vehicle IDs are anonymized. We cannot track anybody. There's no VIN number. So, which means if the data is anonymized, I personally can give the data to the like researchers so that we can improve our safety in our roadway. So that's my comment.
Brilliant. Well, thank you both so much. As we get to the end of this session, looks like folks are starting to move around rooms. I would encourage both of you to put your emails in the chat if that's okay, in case folks think of other questions down the line or just didn't feel comfortable asking a question here during our session. Thank you both. All right, so this is yet only the beginning of BTR. So I would encourage everyone to check out in the chat. We have the other sessions or sticking around in this room for a session on driver behavior choice and demand analysis, and certainly joining in tomorrow as well with a lot more great presentations. Thank you all for coming to our safety session here, and maybe we'll give folks 2-minute bathroom break before we jump into the next round of sessions. Thank you.
Thank you.